Welcome back, y'all. Today in AP Stats, we're going to go over Lesson 4. And Lesson 4 talks about hypothesis testing on two-sample proportion. So kind of think of it as like what we did for the two-sample means test when we have two different population and both populations are testing something, right? I want to give a big shout out to Reese for pointing out in my last video that I forgot to do forgot to write the title of my test. I have it written down on a sticky note and I have it right in front of me so that I can remember to write in the test for all of y'all today. So I just want to go over some changes that I made to the video. In this video, I'm only going to go over the notes and the model problem. I'm going to upload pictures to the practice problem and make a separate video that is optional for you to watch if you feel like you need me to explain the problems to you. You're not required to watch that video, but it is helpful for you if you don't understand what's going on. So let's go ahead and get started. Based on the design of our study, we may be interested in comparing two sample proportions to see if there is a significant difference in two groups' responses or in the effect of an imposed variable or situation. So what that is saying is that we're trying to see if treatments are affecting the two different groups. In this lesson and over the next few days, we will learn how to conduct a two-sample proportion z-test to test whether we have significant evidence of a difference between two proportions. Again, we will follow the same basic four-step model, so they're talking about the template, and the changes for these steps have been highlighted for you below. So as you're looking at your template, it's actually better to look at the template at the beginning of this section. So I'm going to go back to page 6, I believe, of our packet. And page 6 shows us the templates for all the tests. So I'm going to highlight what we're focusing on, which is the two proportions. Okay. And some things that we have. Okay. So our conditions are pretty much still the same. And we're going to think back to our two-sample means test, where when you have two samples, you have to test the normal condition for both of those samples. So in this case, we're going to do n times p is greater than 10 and n times 1 minus p is greater than 10 for both of the samples, for both of the groups. In a two proportion, the parameters, right? You have to do P1 for one of your groups, P2 for your other group. And it's pretty much very similar to what we did with our two-sample means t-test, where we have P1 equals P2, or P1 is less than, greater than, or not equal to P2. And both of these are all P1 hat, P2 hat, etc. Next is our math. So we have a brand new equation for a two-sample, two-proportion z-test. We have p hat 1 minus p hat 2 minus 0. And technically, you don't have to write in the minus 0. That's fine. But what's different now is the standard deviation. The standard deviation has something called p total. And there's actually a mistake in your notes. So I want you to go ahead and correct this. P total is actually equal to x1 plus x2 over n1 plus n2, where the x represents the number of success from each sample. Okay, so for example, if I had a sample of 100 quarters and 25 of the, and I say success means that tails appears, and 25 of those coins shows tails, then what that means is that we have a success of 25. And then all of our conclusions are still the same, except now we say if P1 equals P2, and then the rest of it is still the same. So let's go to our model problem to figure this out. So our model problem for today says that Ms. Tran was curious if the percentage of brown M&Ms were different in the plain bag and in the peanut bag. She wants to run a significance test to prove her claim. She went to the store and bought a bag of plain M&Ms and a bag of peanut M&Ms. She counted the number of brown M&Ms from each bag and recorded her finding in the box below. So I give you this table that tells you of the total number of M&Ms. So in the plain bag, there was 152, and in a peanut bag, there was 124. I got 18 plain ones that were brown and 9 plain ones that were brown. So is the percentage of M&Ms different among the plain and peanut M&Ms? So what this is saying is that we're doing a alternative hypothesis where P1 is not equal to P2. So I'm gonna make the plain as P1 and the peanut as P2. And I'm gonna go through my template first. So I'm gonna create my template. And under the conditions, I'm going to check the conditions. So the condition says that it must be a random sample. And in this case, I'm going to assume that me just going to the store and picking up a bag is a random bag of M&Ms, right? I'm not choosing any bag. It doesn't really matter. I'm pretty sure that this is less than 10% of all of the M&Ms made in the entire world. And now here's the tricky part. The tricky part about doing a 2-sample proportions is that they don't always just give you what the percentages are. They tell you the number of success. But that's fine, right? So I'm going to start with the plain. And I'm going to think about success and failure. And failure. So remember that success is the same thing as saying n times p. And failure is the one where it's n times 1 minus p, right? So in the plain bag, we had 18 success because we are saying that a success is a brown M&M. And in the peanut one, we say that the success is 9 because we had found 9 of them. Now, failure is just taking the total, so 152 minus 18, to give us the number of M&Ms that were not brown. So in this case, 152 minus 18 is 134. And for the peanut one, it's 124 minus 9, which is 115. Now, we need to check that all of these are greater than 10. And most of them are, except for the 9. It's not 10, but it's close enough. So I'm going to say that it's normal. Okay. Next, parameters. Remember that for a 2-proportion z-test, we need to find both of our proportions. So P1 is the true proportion of plain M&Ms that are brown. And P2 is the true proportion of peanut M&Ms that are brown. Okay. And there was a little bit of a mistake in your template. Your template says that HO is P1 is equal to P at 2. We're actually just doing P1, P2. So HO is P1 equals P2. And this is always the case for a 2-sample proportions. And we're saying that there is a difference in proportions between the two. So there is a difference in the number of brown M&Ms. Now, I already made my mistake. I see my sticky note, so I'm going to write this down. The name of this test is a 2-proportion z-test. You can also say a 2-sample proportion z-test. Both are correct. Next. Math. So for the math, I like to calculate all of my variables first. So P hat 1 is equal to the number of success, meaning the number of brown M&Ms for the plain bag. So that's 18 over 152, which is 0.12. P hat 2 is 9 over, I'm going to write this a little bit bigger, 9 over 124, and this is 0.07. Now we need to find something called P hat total. So P hat total, remember, is x1 plus x2 over n1 plus n2. And I like to think of this as like the average between P hat 1 and P hat 2. So x1 represents the number of success from the first population, which was 18, plus the number of success from the second population, which is 9, over the total number for the sample size. So that's going to be 152 plus 152 plus 124. And this gives us P total to be approximately 0.1. Next, Z equals P hat 1 minus P hat 2 minus 0 over the square root of P hat total times 1 minus P hat total over N1 plus P hat total times 1 minus P hat total over N2. I'm going to plug all these numbers in. I'm sorry that this is cutting off because there's a lot, I needed a lot of space, and I get my z-score to be 128, okay? So this means that my p-value, and I'm going to write my p-value up here because I'm running out of room, p-value is about 0.2023, okay? And remember that because we're doing not equal to, we're shading both sides. Okay, so I'm going to show you all how to use your calculator to do the two sample proportion z-test. So we're going to go ahead and go to stat, go over to test, and then go down to two prop z-test. Okay. So two prop z-test asks for x1, n1, x2, n2. So x1 is our number of successes. So in our model problem, right, our number of successes was 18 brown M&Ms with a total of 152 brown plain M&Ms. Okay. In the peanut bag, we had 9 M&Ms out of 124 that was brown. We set our alternative hypothesis, so we said that P1 does not equal to P2, and then calculate. And so if we calculate this, it gives us a z-score of 1.275, so I rounded that to 1.28. P is equal to 0.20. It gives you P hat 1, P hat 2, as well as P hat total, right? So if you're having trouble calculating what P hat total is, use your calculator. Don't try to do it by hand. So our conclusion, if P1 equals P2, then the probability of our sample difference or extreme, and we use or extreme because, or more extreme, because we're doing P1 does not equal to P2. Is 20%. Since P equals 20% is greater than alpha equals 5%, we fail to reject HO and do not have have evidence to support that the proportion of brown M&Ms are different. Okay, so we do not have evidence to support that the proportion of brown M&Ms are different, and this is because P is greater than alpha. Here's an extension question. How would your p-value differ if you ran a one-tail test instead? Why does this happen? Would your conclusion change? Well, first, we need to remember that a two-tail test means p-value was doubled, right? So if this is our curve, both of these p-values add up to 20. So each little section is 0.1. So if HA was saying that P1 is greater than P2, we're just looking at this little tiny section here, so this is 0.1. If we're saying P1 is less than P2, then we're looking at everything else. And if we remember that this little section is 0.1, so 1 minus 0.1 equals 0.9. So our conclusions do not change since both of these percentages are still bigger than alpha. Okay. At this point now, we're going to do a check for understanding. I'm going to read the problem, read the question, pause to let you answer the questions in the video. I'm going to give you the answers and then do the same thing for each of the questions. The movie A Civil Action tells the story of a major legal battle that took place in a small town of Woburn, Massachusetts. A town well that supplied water to East Woburn residents was contaminated by industrial chemicals. During the period that residents drank water from this well, a sample of 440 births showed 16 birth defects. On the west side of Woburn, a sample of 228 babies born during the same time period revealed 3 with birth defects. The plaintiffs sued the companies responsible for the contamination, claimed that the data showed the rate of birth defects was significantly higher in East Woburn, where the contaminated well water was used. One may want to try to use a z-test to try to prove the evidence for this claim. Why would running this test not be advised? And here's a hint. You want to think about your conditions. Okay. So go ahead. A check for understanding is going to pop up now, and you're going to answer this question. Think about the conditions. Why shouldn't we use a z-test? Well, a z-test, and if I'm telling you to think about the conditions, right? The conditions tell you that n times p and n times 1 minus p must be greater than 10. Well, in East Woburn, the number of birth defects is 16. But in West Woburn, there was only 3. 3 is less than 10, so the sample isn't normal. And since the sample is not normal, we can't use a z-test, right? Remember that the z-test and t-test are only for normal samples. Using a more advanced statistical test, it was found that the p-value for this situation is 0.0185. Explain what this p-value means in context to this situation. So here, you're just writing the first part of your conclusion. You're not telling me what we're doing to the hypothesis, okay? What is the first part of the conclusion? What does this p-value mean? Well, this p-value says that if the proportion of birth defects are the same, then the probability of our sample difference or more, because we're saying that East Woburn has more birth defects than West Woburn. The probability of our sample difference or more is 0.0185. So there's a 1.85% chance of this happening. Okay. Now, based on this p-value, what conclusion would you make about the situation? Go ahead and answer that question now. Well, since p equals 0.0185 is less than alpha equals 0.05, we reject HO, and there's evidence to show that East Woburn has more defects. What error could you have made based on this conclusion, and what would the consequences of this error be? Go ahead and answer that now. So since we rejected HO, this is a type 1 error. And a consequence of this is that the company gets sued when they did nothing wrong. Okay. That is it for today's video. Go ahead and do the practice problem. If you need help with the answers to the practice problems, there's a video that I'm going to include in this Google post.